25 plus years experience spanning academia and health technology translation, including 4 years in assistive technology, SME charity, disability. She holds a PhD in computer science and MSc in biomedical instrumentation engineering and a B Engine with honors in electronic systems engineering. She leads the CHAT research group, delivering interdisciplinary research programs focused on evaluation, safety assurance, and adoption of robotics and connected health technologies. Her governance and standards roles include co-chair of the IEEE REH Technical Committee on Robot Ethics and membership of ISO TC 299/WG2 and UK BXI Robotics Ethics Committees. She led the EPSRC Healthcare Technology Network Plus Emergence, which has produced a white paper on robotics in health and social care, and co-leads the NIHR Rehab HRC Enabling Participation Team. She's also a co-founder and director of robotics for Good CIC, supporting responsible development and deployment of robotics and AI for public benefit. Professor Praminda, you have the floor.
Thank you so much for that introduction, and definitely both Lucas and I'm sure I speak for Lucas, he's still there, will be absolutely thrilled to invite you. I saw some of the really interesting questions about if your background is computer science, what you need to do to get into robotics, and if you're a medical physicist, what you need to do. And I think it'll be really interesting. Lucas wanted, we can host a webinar as well, where we can introduce you, we can link you into our lab with some of our telepresence robots and give you a tour. And yeah, we do look forward to our collaboration. So thank you for that introduction. I'm going to do a screen share, and let's see if I get this right, because I need to share sound as well. So I thank you for that introduction. You know my background, and you know I've trained as an electronics engineer, biomedical engineering, but did computer science and went into that route. And so I think robotics is one of those areas whereby if you have multiple disciplines where you've trained or you've had opportunities to have experience of, it just makes you all the more strong because it is such a diverse area. So I'm going to start by giving a little bit of background on my research group. I don't know if Lucas might have introduced that already, so I won't say much. There's a little link to it. Go and explore, and then like I said earlier, we'd love to host you and to make a strong collaboration with you. And then I'm going to go and talk a little bit about assistive rehab robot embodiments and why we have a robot at all. That's what I'm going to start with, particularly in the area of healthcare and assistive in the home, because care is a relational and human aspect of our humanity. So we have, you would have seen I'm part of lots of ethics committees, and for me it's really important to question when and where robots are appropriate to use in care. And then I'm going to share with you some cases for intelligent sensing, why we have intelligent sensing. And this is where I hope you'll be able to make links with your own backgrounds. And then I'm going to share 3 key insights and some future research opportunities. So to start with, I'm leading this research group. We're a vibrant research group, 9 of us, so with research fellows and almost 20 PhD students between us. And we're looking at all aspects of the use of robotics. First and foremost, safety. It defines everything. If these robots are going to go out in the wild with people in their homes, in hospitals, safety and reliability and checking that through benchmarking is key to everything. And then keeping the user in the loop, keeping healthcare professionals in the loop through user-centered design methods is fundamental to ensuring these are successful in how people want to use them, where people want to use them, and being able to understand that requires specific structured methodologies to be able to develop and incorporate these. And so following up on that, we look at ethics and responsible research. We've got smart sensing, and embodiment. And Lucas, you would have heard from Lucas's talk, specializes in those areas. Autonomous guided manipulation, so being able to control these robots locally in dangerous environments remotely is key. And then another way we've been getting these robots out quicker into the real world is through very basic platforms that can be controlled remotely for telepresence. And this is very significant in work with rehabilitation and disabilities because it allows people to access areas they wouldn't be able to go to physically themselves. And then we're looking at different ways in which people can control these robots, and then about the robots themselves, the mechatronics aspects of how they are constructed, how they move, how they're controlled. And we're very fortunate in terms of the research group. I joined Nottingham 4 years ago, actually now just over 4 years ago. And we've got access to a range of different medical and healthcare technology innovation groups and expertise. So as engineers, we are actually groping around in the dark until we connect with patients, until we connect with the healthcare experts. And this Nottingham offers an opportunity to connect to experts in a number of areas, and particularly through the Center of Healthcare Technologies, which is how myself and Lucas are here in front of you today. It was through Dan Clark, who has been leading the Center for Healthcare Technologies, put us in touch with you. And so these close relationships are further cemented through getting clinical and regulatory expertise through hospitals in the local area. And where is Nottingham? Where in the world is Nottingham? How many of you knew where Nottingham was? Did you look up where Nottingham was? So we're sort of in the heart of the country. I don't know if Lucas, you covered where was Nottingham. No, good. And Nottingham is an interesting little town. Does anybody know from this picture what Nottingham is famous for? Slight myth and slight reality. Does anybody know? No, Robin Hood. Have you all heard of Robin Hood or seen the movie? Yes. Yep. So Sheriff of Nottingham was also always after Robin Hood. And I was looking to see where you are, if all of you are indeed in this place. And if I started to drive, it would take 95 hours non-stop. And it's very interesting. I'd never thought of this before when I realized the time difference. You're in the same time zone, which actually makes collaboration much, much easier than trying to do this with people who might be 8 hours ahead or 8 hours behind. So this is another opportunity for us. So the need for robots within health and social care. One of the things that we look at is where is the appropriate point in which to introduce different types of technology and technological interventions. And we know today health and social care has an urgent need for radical solutions to address so many challenges that we face. And what we're trying to do, we see why we're trying to introduce robots, at least in the UK. I don't know what the situation is in Nigeria, but we have an acute shortage of health and social care professionals. We have a changing demographic in the UK, whereby we have an inverted pyramid of more people living longer, not necessarily more healthily, but having issues resulting in social isolation because it's sometimes in rural places. There are, at the moment, the healthcare system in the UK has been more reactive rather than preventative, which is changing now. So, but there has been no reliable set of interventions to reduce hospitalization. So it's only when people have a fall or an accident or due to long-term health conditions is that when they go into hospital and then everything implodes because there's not enough capacity and resources to support them. So the healthcare model at the moment doesn't facilitate self-management of long-term conditions. And also in terms of rehabilitation support at home, there is not much there. Now, there are some robots in hospitals in the UK, but these have been introduced in more structured ways. So, hospitals that are used for delivery of food, we're seeing these surgical robots have been around for a long time, lots of success with those, cleaning robots. But all of these robots are working within very narrow and controlled environments with experts. So we are seeing introduction of robots within healthcare, and these are from a rehabilitation point of view. Again, very controlled in controlled environments with experts. So what are we trying to do? One of the things I'm trying to do is trying to move or shift the support earlier in this patient journey. So before they get to hospital. So support health and social care professionals with decision making along the full journey, but provide support earlier on in the patient's before they actually become patients, when they start to show signs of problems. So start to use smart sensing in the home at an early stage to be able to detect changes in behavior and long-term conditions, so we can help people with the use of robots in the home self-manage their conditions. So use of embodied AI to for risk mitigation to reduce hospitalization. And then, if they do get to hospital, enable self-management of long-term conditions. So this is what we're trying to do. And to date, there have been lots and lots of robots. And I don't know what comes into your mind when you think about robots out and about in the wild. Perhaps science fiction movies, some dystopian scenarios of robots rising. That's what the general public, at least in the UK, gets to see. And it creates a lot of anxiety. So I like to show that there are actually lots and lots of different ways in which people have developed robots, different robot embodiments based on the function that they perform and where that function is being performed. So I've grouped robots according to the types of functionality they provide. So I've got a category there of domestic service robots, which we see out and about now. For delivery, there are robots in towns in the UK doing food deliveries. In Nigeria, have you seen these type of robots appeared? Have you had robots that you've seen for cleaning or delivery yet?
No.
You have they got there yet? Not yet. Okay. One of the things is the difficulty of the different terrains, the outdoor terrains, the network infrastructure, etc., that's needed to be able to make these successful. Even in the UK, there are still a lot of problems, and there are only certain cities where the infrastructure has been particularly thought of in terms of the built environment, so the roads, the pavements, the networking infrastructure, 5G connectivity, etc., to make these viable. And even in the homes, cleaning robots still experience a lot of problems when you have pets and little children and clutter around the house. Another group of robots, so put them under social companionship. They've been around. There is Paro, the seal robot used for people with dementia, has been quite successful in trying to help people calm down because, stroking something soft and furry and cuddly helps to ease stress. And then there are other types of robots, which are these more anthropomorphic or human-like or zoomorphic, look like pets like the Paro, or they're a combination like this buddy robot that can move around. One of the robots that I've been using for many years now before COVID are telepresence robots. So they're like a Zoom on wheels, if you like, and you can remotely control them to move around a remote environment. And these are proving to be very successful in getting people who are in one location to another location. So, like I was saying before, one of the things Lucas and I will plan for later on in the summer, perhaps, is to have you visit our lab through one of these telepresence robots. Some of the other ones that we are looking at developing are ones that offer additional support to do more physical interaction and help around the house, or with help with personal hygiene tasks, such as this prototype, I should say, Panasonic hair washing robot for people who are disabled, so people who are paralyzed, etc. As you can imagine, water and electricity, soap, it won't mix very well, and there are lots of safety concerns and issues, particularly if they were to be used by people who are not trained. And this is something that's really, really important. All of these robots, at the end of the day, are going to be environments where the people who are around them and need to interact with them are not roboticists, they are not engineers, they are people with perhaps absolutely no technical knowledge and know-how. So robustness and safety becomes paramount. We've recently acquired the Stretch platform here in our lab, and this has been used and piloted in America, where it was developed to support people who are paralyzed, and they can control it with head switches or through voice or through gesture to be able to help them pick up things off the floor, bring things to them, play with their kids and grandchildren. So quite a lot of these robots are being developed where physical assistance is about self individual management and agency and control. So rather than other people supporting them, people themselves can do things and help others as well. So for me, a big motivation for the use of these robots is how can we support people who are disabled to be able to get back to work in the workplace. So it's not just about supporting people's health and well-being, it's going beyond that. It's getting them to be able to do different jobs in the workplace. So mobility becomes an important aspect of how robots can offer support. So help with ambulation. I don't know, Lucas, if you showed, Lucas has been using the Leo Walker in the lab to support people and understand how the sensors and the data from here can be used to predict movement and intention, which is something else that we're looking at in the lab. I'm not going to go into exoskeletons and rehab robots in situations which are more controlled together with a therapist who's there to guide the person. They're being used very successfully. And I saw one of the questions in the chat for Lucas's talk, which was, can these help to shorten the period in which people need support? And indeed, with more intensive and frequent rehabilitation, which can be done independently, people can get better quicker rather than waiting for their one appointment once a week to do their exercises. And then part of that is a robot helping to encourage and coach people to do exercises. So we've got lots of robots, and each robot is doing different functions. And then you've got to think about, well, that's all very well and good, but if we're looking to support older people in the home with different levels of aging-related impairments, long-term conditions, it's actually very difficult to be able to say, hey, robot X for person Y, because people are a longer continuum and they need functions that will change with their own condition. So as, for example, with somebody who's had a stroke, as they are doing more rehab exercises, their stroke might get better. They need less and less support from the robot to help them with everyday activities, for example. So the system needs to be able to develop them. And this is where it starts to get, from a researcher point of view, very interesting and challenging, is how do you know? How do you know? And how is the system able to sense and know what kind of level of physical assistance they need and what is the nature of that interaction, the physicality of that interaction, and what kind of support do they need? Do they need help with social interaction, cognitive support, assistance with physical tasks, and or do they actually need physical assistance? So I'm going to show you a little video now of a system that we developed in the lab. And I'm hoping sound is all going to work. So let me know if it doesn't. And so this was a situation which was mocked up in our lab, which is looks like a realistic hospital ward room, to stop people before they get out of bed. And if they've been in bed for a long time, they get deconditioned, so they are more prone to falls. So this is connecting two different types of robots and supporting a patient who is at risk of for fall. So you can see the TEMI robot here and a Kinova Gen 3 light arm. Thermal sensing cameras detect when the person's getting out of bed, which triggers an alert to a robot. So here, rather than having one big robot with an arm, we've linked up two robots together. One acts as the delivery robot, one acts as the robot that can detect things on the table, identify them using computer vision, and carry out tracking, grasping, pick and place. One of the things that's important is to be able to use robots which are practicable in the real world. And if you have too many large robots in cluttered environments, it becomes really hard from a safety perspective and a practical, pragmatic perspective to have these moving around. So I'd like to explore how we can connect smaller and cheaper platforms together. So here there is an opportunity to be able to have and try different kinds of mobile platforms, such as this one, together with arms, and then link them together to carry out different tasks. So I hope you were able to hear the sound from the robots there. Were you able to hear the Temi?
No sound.
It wasn't. Oh, I was sharing sound. Oh no. Oh, okay. I'm going to have to tell you what happened. Temi was speaking to the person, asking what they wanted, and the person told the Temi what they wanted. I'm sure I clicked on share sounds with this, not to worry. And then Temi can speak to the person using voice interaction, and the person can do vice versa, and it communicates with the second robot. So this is a very simple system which is using thermal imaging cameras. You can see there are two. That's the input from the thermal camera, which is at the end of this bed, looking into the bed of the person. And this one at the top right-hand corner is the thermal camera on the ceiling of the room. And so based on some machine learning algorithms, we can detect when somebody is getting out of bed, which triggers a response to the robot to come and support the person. So if I show you the architecture of this, so thermal imaging cameras, one up here, one at the foot of the bed. And this is a very straightforward and simple approach for control of a robot. So you sense what's happening in the environment, you learn and recognize. So a machine learning algorithm has been trained to recognize different postures of the person, different people, and then based on that, it can assist, so it can adapt its behavior. And between the robot and the system, we have a simple messaging system to be able to allow the robots to talk to each other. And I love this example because it is simple to implement, it's cost effective, it requires, it's modular, so you can swap the sensors, you can swap the robots, you can swap the interactions taking place. However, we are now getting to a stage where there is a lot more opportunity with the platforms that are being made available to us and developed. And we can use other things beyond the simple sense, plan, act model. We can have more collaboration and coordination with people and other systems. We can connect between different robotic systems, which is what I've started to do in the lab. The robots can be more sophisticated in their thinking and acting because of more actuation that's available, and the training and learning can be much more sophisticated. And with GPU, high speed processing available in locally rather than in the cloud, it allows more sensing and opportunities for interaction to take place. So I'm going to show you an example of another robot. Now, this is going to be difficult if there's no sound, so I'm going to have to speak on behalf of the robot here. This was a system that I developed at my old lab, which was a ceiling-based robot. This is the first prototype. That's why it looks really bulky and big. But it has to be bulky and big to some extent to be able to support the weight of the person. So it's going to help me, is on the bed, to be able to get out of bed. It is controlled through a Google Home device. So the voice interaction, again, is through a pre-existing technology whereby I can speak to Google Home and it relays my commands to the robot. It's got force sensors or load cells on the infrastructure here, and it's got strain gauges on the two handles, so it can detect when I'm pushing forward and pulling back on it. So the strain gauges help to, for me, rather than explicitly tell the robot to go higher or lower, I can push it forward and backward. And leaning on it means a load cell detects a threshold and it helps me get up. So imagine such a robot. So at the moment, the situation is, at least in the UK, you need to go to the bathroom. Your carer only comes in twice a day for 15 minutes. All the other time, how do you get yourself to the toilet on your own? So we were looking at solutions that can be implemented in the home. So I'm going to play this, and apologies for the lack of sound. But so I'm talking to the robot saying, help me to stand. The robot asks me where I am, and I tell it I'm on the bed. And it says it's going to send it to me. So the motors, it's a XY plotter system on the top, moving the robot. And now I'm saying I want to adjust the robot's position. So it's telling me to move the handles, and I can push forward, and you'll see the robot going down and then going up. So I have to get it to the right height for myself. And I just tell it I want to adjust the position. It tells me to move the handles when I ask it to adjust the position. And now you can see it's going up as I move the handles. And when I'm in a comfortable position, I can communicate that to the robot. And it tells me that when I'm ready to stand, I can let it know. So there's a lot of coordination and collaboration interaction going on between myself and the robot, using voice and using implicit input. So I lean on it, and the leaning transfers my weight over to the robot, which when it knows, it's trained to detect my weight, and it pulls up, and then I can walk forward. So now I'm going to give you a little exercise for you to think about and do. So as medical physicists or clinical engineers, I want you to put on your hat of devices and systems and control and sensing and think about this situation, okay? Imagine I'm a patient who is very ill and frail. I might be in my dressing gown. I might have a catheter. I might have a stoma. I might not be able to see very well or hear very well. I might have pets around the place. This robot's in my home helping me to get to a bathroom. It might be urgent and might need to go very quickly, and nobody else is there around me to help. So I would like you to now, I think we've got a little bit of time Although I see I'm coming to the end of my 11:30 night so maybe we'll just end with this exercise. Is So I hope you can access through your phones the QR code, which will take you to being able to answer some questions. So I want you to think about, based on that video, what are all the things that the robot has to sense? Yes. So think about the situation and that person that I described who is very ill and frail, needs to get to bed quickly, might be on medication. What all does it need to locate? So it located me on the bed. So it asked me first, sorry, you couldn't hear the sound, where I was. I said I was on the bed. But what else would it need to locate? What are the different things such a system needs to think about? Is everybody able to access the quiz on there? Can you let me know so that you can start answering these questions?
Yes, somebody has helped to put this in the chat, the link. So I believe
Okay,
everybody
great.
has it, yeah.
Okay. All does it need to connect with? Now think about this system and where it is in the home. What other sorts of system would it need to connect with? Yeah. Think about if there's an emergency, or if I start to feel drowsy as I'm getting up, or maybe it needs to know if I'm on medication or not. So what does it need to connect with? And then think about all the different aspects that it needs to collaborate with me on. Yeah. So in that coordination, which is actually quite a dangerous movement, that transfer from bed to standing for a patient who might be weak and frail, lots of things can go wrong. So what is that collaboration about? What are the different things it needs to learn about me, about the environment? Try to be specific with the example that I've given you about the patient. And then what are the different actions that can take? Obviously, the one was about coming to me and then moving into the right position. So it's at the right height for me to lean forward and to take my weight. What else? What other actions might it need to perform? Imagine if I had pets or grandchildren or the lights went out because there was a power cut. And when you've done that, you will see if you go back and think again about all the things that the robot has to sense, there'll be a lot more. So what I'm going to try and do is, let's see if I can get to the quiz itself to see how people, so just put in a couple of words. Let's see what kind of answers are appearing. So I'm just going to go over to this and have a look to see what answers are appearing. Okay, we only have one response so far. Come on, people. How many of you are on the call? Try to put some more in. But good answers so far. So we have vision, yep. Sound. Sound is an important one, which people often forget. So very well done for that. The ambient sound and noise would interfere with my voice interaction with the person. So this needs to be able to sense if the television or radio are on and be able to distinguish between me, my voice, my instructions, and the ambient noise and sounds in the environment. And it's never always going to be very quiet, like in a lab condition, which is something else we forget when we're developing these systems. Touch, yes. Temperature, that's a good one. Temperature can be important because it can affect the performance of the cameras. If there was a thermal imaging camera, which we sometimes put on for privacy preserving, because people don't like to have a ordinary camera, especially if they're in their undergarments in bed, etc., then the temperature would affect the calibration of such a system. Yeah, the time of day, yep. Force, very good. Let me just refresh to see if there have been more responses there. Yep. So pain, very good. That's an extremely important one because the characteristics of how the robot will move and adapt, so the speed with which it does would need to be modulated according to the level of pain the person's experiencing. And then we've got, what does it need to locate? Yeah, what the need is for people, I think is sort of saying obstacles. Yes, definitely. And the destinations and how people name those destinations. If I say I'm on the bed or I'm near my pillow, what else does it need to locate? What else is in the way? My slippers or shoes or a chair could be there. My walking frame, my other devices might be there. So quite a lot more. Yep, the barriers. What about this now? What does it have to think about? Yes, this is where the learning comes in. So what it needs to think about based on what kind of issues, the condition of the patient, yes, seriousness. Somebody, you said, talked about somebody mentioned pain. So I think one of the things it needs to think about is how is the pain, what level of pain, how is that going to affect the patient? Could they lose their grip? Could they get dizzy and fall? All of these things have to be think about. Yeah, medication, where they want to go, how urgently they want to go as well. And then what it connects with. Oh, that's good. I can look at it in more detail there. This is an interesting one around the planning and decisions in terms of thinking will vary from patient to patient. And you'd have to configure the system to make sure that it addresses those. I think I would say connect with patient healthcare records. So yes, so it needs to know about the weight, the cognitive level, very good, mobility levels, and it needs to collaborate on understanding if the person is feeling able to stand up at that time. One of the things that can happen is people think they can stand up, they start to stand up, maybe it's too much pain or they're feeling too dizzy, and they have to sit back down. So that coordination is a really important part of this. What else have we got here? We've got, so it needs to learn about that. Yep. The speed, condition, strength of the patient. That's a really important one as well, because sometimes people might be too weak. The system might have been trained on the person at a point in time where they were able to manage, something's changed, and you need to be able to adapt to that very quickly. What else have we got? What different actions does it need to be able to take? Yeah, so it needs to be able to move in relation to the person, yeah, the assistance in standing. But some of the other things that it might need to do is to be able to mitigate against things that happen were unexpected. So the patient starts to fall. What should it do? Or if the power is cut or one of the sensors gets compromised, how should it respond? So we always think about quite a few of the functions and what the systems need to do. We call them mission control functions, so what it's designed to do. But sometimes we forget to think about the non-mission part of the functionality, and that's really key and important. I'm so pleased to see all of these responses because I can see it's really getting you to think about exactly as I had hoped in more contextual issues. So please keep continuing to do that, and maybe you'll have the opportunity to look at these again. And so, in terms of one of the key things that we do in terms of the research in robotics, assistive robotics, is being able to understand hazards and risks so we can preempt these and design in mitigations and features in the system that can help us address them. The real world is has a lot of uncertainty. It's very noisy, and people change, and their levels of impairment change over time, over the period of a day. And the systems where it's going to be used can have added complexity if that system is cluttered, if it's noisy, if the light levels are not very good, etc. So the first insight, and I think I'm going to finish with my first insight, and because I think we've got Unito Hoppus 11, isn't it, Tariboso, and I don't want to hold up the rest of the proceedings, and I'll be happy to continue this at some other time. The first insight is start from care. Think about the patient. Safety isn't just about trying to avoid collisions and things like that that you find in robotics. It's about designing interactional safety. So designing controllers and policies that respect human limitations in context and that can gracefully back off when the person cannot and should not proceed. So I was very pleased to see your responses were thinking about the person, the medication levels, the pain levels, and what needs to happen to find out about these. Is it implicit? Should we be designing sensors that can sense this themselves? So maybe we need to have more integration with biomedical markers or sensors within the body, on the body to be able to sense it, because the person might not always be able to tell you how they're feeling. The system should be able to deduce that from putting all the sensors together. So safe autonomy, safe autonomous implementation requires adaptive interaction that explicitly tracks human collaboration and can slow down. It can ask the person, it can defer, or it can replan. And to be able to achieve this, we have to think about the person in the loop, the fact that we can make a lot of errors in the development of these systems if we don't consider the person and the context and the issues in questions. I'm going to jump to one of my later slides, which is around human-robot failure taxonomy. So I've been doing work on trying to think about, in a system, it's not just the sensors that can fail and the controllers and the mechatronics, it's us. It's our lack of concentration, it's our lack of training. And if these systems are going to be used with us, we need to start to think about, hey, how do we understand these and how do we design and preempt for them? So I've been doing work looking at systematic approaches to be able to do this kind of error analysis. And it is very comprehensive. It needs to be very comprehensive because you need to ensure reliability of these systems. So you need to have thought through in a methodical way what could go wrong. So we've been using this approach called STPA, Systems Theoretic Process Analysis, which can break down the task into subcomponents and tasks and then work through the dilemma of decision making in an ambiguous world where we might say something, we might mean something else, sensors might misinterpret the data. And one of the questions to Lucas in his talk was about detecting the EMG, and Lucas said it's really hard to detect intentional movement from unintended or other movement. And that is a challenge. And the more these systems operate in the real world, the harder it becomes. So what are we doing? We're working through this in a systematic way and trying to understand and build a safety argument strategy where the claim that risk has been reduced is done in a comprehensive way so far as it's reasonably practicable, which means an exhaustive coverage of potential hazards. And this is where we are now able to leverage the large language and vision transformer models. So I've been working on research where I've been reconstructing the real world in simulation environments. This is the work of one of my master's students. And we've been recreating hundreds of thousands of situations and getting the large language model to analyze these and then deduce. Don't try to read these, it's just to show you the comprehensiveness of this, is repeating over and over again. What are the issues? What can go wrong in the interaction? What should happen? What's the severity of that risk? And through this approach, we can then start to develop the mitigations for safety. But safety goes beyond just physical risks. There are lots of other risks. And as part of my work on the BSI Standards Committee for 8611, I've been looking at ethical risk assessment of robots. And there's a paper you can access on reading more about that. And with that, I will just get you to think about what the future research opportunities are. There's lots of work to be done here before we can get these robots out safely in the world. Improving approaches for situational awareness is my top one. So being able to do this through real-time sensing on edge devices, so you can do more quick real-time and more comprehensive real-time analysis of lots of different sensors. Also to address ambiguity, integrate with multimodal sensing, integrate sensors in smart materials, so the system itself is inherently smart. Developing embodied models that learn from implicit interactions rather than explicit, and safety design features that encode human factors, particularly error, to lead to improved reliability. And with that, I've got some questions for you. This is being recorded. You can think about this, and hopefully we'll have the opportunity to discuss these in more detail later. Thank you very much from myself and my research group who make this research possible.
Thank you, Professor Praminda. That was a mind-blowing presentation, I must say. With everything you say pertaining to the applications of robots for domestic service, social companionship, extended living applications, mobility, and rehabilitation. One of the things that catches my attention is the exoskeleton. And I
Yep.
believe such can be used in the hospital if deployed for the management of patients, most especially during and after the administration of radioactive iodine.
Yes, indeed. And one of the things I was seeing, I'm very excited about this. I recently visited China and went to see the Great Wall. And at the bottom of the Great Wall was a kiosk. And the kiosk had a number of exoskeletons, lower body exoskeletons, where you could take one out with a QR code on your phone, pay for it. It was costing about 35. I converted it to pounds per hour. You fit one on, there are very clear instructions, and somebody who might have problems with their knees or their hips can put one of these on and can help them. Now, this is not in a medical situation, not a healthcare situation. It's just in everyday life. And I think this is what we need to be a bit more bold about, trying to bring these technologies out and test them. And to be able to, and this is where my emphasis is at the moment, to be able to do robust benchmarking and safety analysis, risk and hazard analysis and mitigation, so that when this person puts it on at the Great Wall of China and tries to go up, it's not going to fail. And if it fails safely.
Okay, I will just take some of the questions from the chat box. One of the questions from the Goodnets, she said, just a minute. Say, how far have we gone in solving the sample efficiency problem? For instance, some humans can learn some things within hours, but an AI needs decades of simulating to reach the same level of safety.
Yep. So one of the things that I didn't show you on my slides, maybe we can have another talk, was we're working with digital twins. So what we do is we collect data in our labs, and actually I will just see if I can quickly show you that to answer that question. So it's very difficult to get patient data, and so one of the things, I think I'm still sharing my screen, we do is we construct a model of people. We started with where a person wearing a simulation suit, a stroke simulation suit, which simulated hemiplegic stroke, which is one side of the body is people find harder to move. We also had them wear an eye patch to simulate neglect on one side, because sometimes people with stroke see off one side. And we got them to move around a real space and collected a lot of data on their gait and mobility. And through this, we were able to model somebody walking with a rollator and understand how they move and turn based on their disability. And by building this initial model in simulation, we are then able to try out different what if scenarios and be able to distinguish between people with and without hemiplegic stroke. And so the next stage now, we're collecting data from real people in a residential care home here in Nottingham, where we are then going to use and build on this existing model. So the question relating to lack of data is actually a really big one. And some of the approaches that we need to consider is how do we build these digital twin systems which we can then use to play out what if scenarios. So what if the rollator starts to move forward? Because we've got a model of the person using a rollator in different environments and now with different characteristics, we can tweak parameters within that model, make the rollator move faster, see what will happen if the person starts to get dizzy and put too much force on the rollator and the rollator starts to wobble a bit. We've got IMUs on the rollator and in our model as well. So one of the things is digital twins can help you with this problem of not having access to enough data and being able to run simulations faster.
All right, thank you, Prof. Still have another question. Considering how rapidly AI is advancing, do you think AI integrated robotics will significantly shorten rehabilitation time for people with disabilities? For example, improving hand function, mobility, or vision assistance compared to traditional recovery process?
Yes, absolutely. Really important point and a motivation for developing these technologies. So, well, the key issue with good access to rehabilitation is people are not able to get enough time with physiotherapists, rehabilitation expert to be able to carry out the rehab, but using a system which can allow you to repeatedly carry out the rehab exercise, say upper limb rehabilitation or walking, at your in the time where you can do this by yourself. So the intelligence system can monitor you carefully and adapt your program. Obviously, there has to be coordination with an expert. And this is one of the challenges. If the system starts to adapt your rehabilitation program and injures you by overexerting you or taking your arm out of a safe motion, which for you could be very limited due to your disability, your pain thresholds, etc., that could be a problem. So this is a really good case for a system that's intelligent, that can monitor, and that you can collaborate with, that you can talk to, or you can gesture to, or you can make actions and speak to, or it can sense you to be able to then ensure that the rehab is being done safely and in a way that is progressive to suit you. So indeed, lots of opportunity to accelerate your recovery process. However, the intelligence systems need much more work at the moment to make sure that they are safe to be able to use independently.
Yes, Prof, there are some of the questions in the chat box. I don't know if you can just attempt to one
Yep,
or two before we go. Yes.
yep. Okay, okay. So well, the high cost, yes. Scalable or cost effective. Actually, that has become one of the key motivations for me in thinking about what do we mean by cost effective and scalable. Now, there is a tricky situation here because for these systems that have to operate independently in the world, they have to be safe. For safety, you have to have some level of redundancy in the system. Yeah, so if one part of the system fails, then you can pick up that information or the data or the processing through another system. Also, the sensors have to be reliable. You've got to be able to ensure that they operate for long periods without too much need for calibration, or then should we be able to use the machine learning to be able to use low-cost devices, more of them, to make them safer to work together. But how would that affect the reliability of the system? If you're there on your own in your house and you had that Chiron ceiling-based robot, if it was too cheap in terms of it was using low spec sensors that might be prone to variations from temperature or might need to be calibrated very often, or had a very narrow, reliable operational zone. Well, you wouldn't really want to leave that with a patient, would you? So there is this sweet spot and this problem whereby you can have machine learning to compensate for some low-cost devices, and then but you can't go too far with that. So there is this, and this is a challenge for us engineers, I think, is how can we leverage machine learning to help make low-cost sensors and systems work more efficiently and safely together. Okay.
Thank you, Prof, for your time. We are grateful.
And yeah, so I've answered the question on simulation and that's true. Digital twins. Yeah, there's AI in radiation nuclear emergency. One of my colleagues, Aisha Kuklamaz, do have a look about her and her research from our website. She's looking at developing teleoperation systems for nuclear decommissioning, so remote operation of robots in dangerous environments. The limitations, I guess, are around being able to do very intuitive control of these robots remotely, because human beings, again, there's a human factors issue, can't focus for too long in sorts of those environments, and the ask for a human to be controlling this becomes very hard. So one of the things she's looking at is looking at shared control and shared autonomy. So reducing the workload on the person so they don't directly have to control every single movement, but let the robot take over some of the control, and then the human maybe just directs the robot. So definitely this is a key area, dangerous environment where robots come into their own. And okay. Are there any other questions people would like me to pick up on? Oh, the biggest gaps. Yes, yes, yes. Thank you for answering that. Yeah, adaptability, power, and battery life. I think that's going to be fundamental moving forward. Quite a lot of people I know who use manual wheelchairs do that just for that reason, because they don't want to get stranded when the battery runs out and then they have no other way to move. So we do have to think about maybe energy harvesting is one of the key areas, I think, in terms of foundational scientific development, which will contribute a lot to this. So thinking about people in the University of Bristol are looking at energy harvesting through the movement and the motion of the devices themselves, through smart floors that can pick up your movement on the floor and harvest energy through that. So yes, yeah, safety, positive experience over time with trusting a robot. Yes, but it'll be nice to delve more into what that positive experience means. And that trust element is one of the biggest barriers from a adoption perspective, to convince people that you will be okay, your jobs will be okay, it'll just help to make your lives better, and what the safety features should be. So we're doing a lot of work. I was a part of a project on benchmarking robots. So particularly in assistive scenario, and you can find one of the papers on our projects there, the different ways in which we use competitions for benchmarking robots. So we say your robot has to be able to perform this task in this particular environment, and we get students to develop their technologies and take part in competitions. And if you're interested, there are quite a few assistive robotics competitions, and that's a great way for you to get involved in making and understanding robots and the issues of operating in the real world. So competitions for doing benchmarking work is becoming quite a big area. And are there parameters to be put into before using? Yeah, so one of the things, so this is a question, are there parameters to be put into consideration before using a robot AI system for other patients? Extremely important question. And one of the things I get very irritated with when I read papers, sometimes they talk about the older person, or they talk about the stroke patient. But we know no two people are the same, and it is a responsibility of the engineer to actually define very clearly who the patient is, who the target patient is. Is this technology appropriate for them? What stage of their condition is it appropriate for? What is it actually going to target? I think we need to do a lot more work on being clearer in the technologies that we develop as to who they are most suitable for and when is the best time to use them and how. Okay. And the other burning questions? I think I've gone well over my time. I'm sorry to the other speakers to keep them waiting, so I think I should stop. And it's
You're
spring here.
actually our last speaker for the day. You are the last
Oh,
speaker
okay.
for the
Okay.
entire program. So
Well, so I should ask you. I'm still seeing lots. Oh wow, 68 responses. I am so impressed. So I'm just going to do a quick screen share, and I'll be happy if you're happy to share all the different things that you have put in this response. So I got 68 responses and some extremely interesting and well thought out things. So I think from what I'm reading here is your summer school has been extremely successful, and you're really switched on and thinking about the various issues. And I speak for the chart group, would be very keen to collaborate with you in the future.
yeah,
Yes.
that'll be exciting.
Yeah.
We look forward to that.
Very, very impressive. Look at that. All the different things you've been thinking about.
Mhm. I am even still thinking. I couldn't even answer the questions. I was still thinking because the first thing that came to my mind was this robot must be very confused, you know? So I couldn't even answer the question. I'm still thinking. I'm going to take time. I'll look at the form again and take time to answer my own question. So I'm happy that 68 people could answer the questions. So
Yes, no, very,
that's
very well
good.
thought through.
Because I was stuck in my head. I was like, this robot has a lot of things to figure out. So
It does indeed. It's going to keep us all busy for many years to come.
mhm. Thank,
Okay.
thank you so much.
Oh, I was
Thank
just
you
going to
so
say
so
it's
much.
spring here in the UK. So I've got daffodils from the University of
Ah,
Nottingham from our
nice,
park campus in my background.
nice,
So
nice.
I wish you all, yeah, the very best, and I hope our paths will be crossing again.